Where did everything come from? It's the most fundamental question humans have ever asked. Not just where did Earth come from, or the solar system, or even our galaxy. Where did space itself come from? Where did time begin? What existed before the universe? Tonight, we'll explore the most profound origin story science has ever told, the story of the Big Bang, the moment when everything began. We'll journey back to the very first instant of existence, when the entire universe was smaller than an atom, infinitely hot, infinitely dense, containing all the matter and energy that would eventually become billions of galaxies. We'll witness cosmic inflation, a period when the universe expanded faster than light, growing from subatomic to astronomical size in a fraction of a second. We'll see the first particles form as energy condensed into matter. We'll watch as the universe cooled enough for atoms to exist, releasing light that still fills space today. We'll explore the cosmic dark ages, when the universe was filled with hydrogen but no stars yet shone. We'll see the first stars ignite, massive titans that lived fast and died young, forging the first heavy elements. And we'll trace the evolution from that brilliant beginning to the vast, structured cosmos we inhabit today. This is the story of creation, not myth or metaphor, but the scientific account of how everything we see, touch, and are came to be. It's a story 13.8 billion years in the making, and it begins with the ultimate mystery, the Big Bang itself. To understand the Big Bang, we must first confront a paradox. What came before? It's a natural question, but it might not make sense. Time itself began with the Big Bang. Asking what happened before time existed is like asking what's north of the North Pole. The question contains a logical impossibility. But let's explore what we know and what we suspect about the origin of everything. The Big Bang wasn't an explosion in space. It was an explosion of space itself. Space and time emerged together from an initial singularity, a point of infinite density and temperature, where the laws of physics as we understand them break down. The word singularity might be misleading. It suggests a specific point in space, but there was no space for it to be in. The singularity was space, all of it, compressed to a mathematical point with zero volume and infinite density. This concept is difficult to visualize because it's unlike anything we experience. In our everyday world, things expand into existing space. But in the Big Bang, space itself expanded. There was no pre-existing void for the universe to expand into. The universe is everything, all of space, all of matter, all of energy. Outside the universe, the concept of outside doesn't exist. General relativity, Einstein's theory of gravity, describes how space and time curve in response to matter and energy. When we run general relativity's equations backward, tracing the expansion of the universe in reverse, we find that everything converges to a point about 13.8 billion years ago. At that moment, density and temperature become infinite as singularity. But can we trust this conclusion? Probably not entirely. General relativity breaks down at the quantum scale, and a singularity is inherently quantum scale. At the smallest distances and shortest times, quantum mechanics must play a role, but we don't yet have a complete theory of quantum gravity. So while we're confident the Big Bang happened, the evidence is overwhelming. The exact nature of the initial singularity remains uncertain. It might not have been truly infinite. Quantum effects might have smoothed it out, creating a finite but incredibly tiny, hot, and dense state. Some theories propose that the universe didn't begin from nothing. In eternal inflation models, our universe is just one bubble in an infinitely larger multiverse. Inflation, a period of exponential expansion we'll discuss in detail, is eternal, constantly creating new universe bubbles. Our Big Bang would be the moment our particular bubble nucleated from the inflating background. Other theories suggest a cyclic universe that repeatedly expands and contracts. The Big Bang we observe would be a bounce from a previous contracting phase. The universe might be eternal, with no true beginning, just endless cycles. Then there's the question of why the universe exists at all. Why is there something rather than nothing? Some physicists suggest that nothing is actually unstable. Quantum fluctuations can create particle-antiparticle pairs from vacuum. Perhaps the entire universe is a quantum fluctuation on a cosmic scale, a spontaneous appearance of everything from nothing, allowed by quantum uncertainty. Lawrence Krauss popularized the phrase, "a universe from nothing." Though philosophers debate whether his nothing is truly nothing or just a quantum vacuum with its own properties and laws, the fine-tuning problem adds another layer of mystery. The universe's fundamental constants, the strength of gravity, the mass of electrons, the speed of light, seem exquisitely calibrated for life. Change any of them slightly, and stars wouldn't form, atoms wouldn't be stable, or chemistry as we know it couldn't exist. Is this fine-tuning evidence of design? A cosmic coincidence? Or are there countless universes with different constants, and we simply exist in one of the rare universes where conditions permit life, a selection effect called the anthropic principle? We don't have definitive answers. The ultimate origin of the universe remains one of science's deepest mysteries. But we do understand, with remarkable confidence, what happened after the beginning, the evolution of the universe from its earliest moments to today. That story begins an incomprehensibly short time after time itself began at 10⁻43 seconds, the Planck time, the shortest meaningful interval of time in physics. Before this, our theories fail. Space and time might not have existed as distinct entities, but at the Planck time, the universe entered a regime we can describe, at least approximately, with our current physics. At this moment, the universe was unimaginably hot, about 1032 Kelvin, and unimaginably small. All the matter and energy that would become the observable universe, billions of galaxies, each with billions of stars, was compressed into a region far smaller than an atom. The four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, might have been unified into a single force. As the universe expanded and cooled, these forces separated, one by one, like water condensing from steam, a process called symmetry breaking. First, gravity separated, becoming distinct from the other forces. Then the strong nuclear force split off. Finally, the electromagnetic and weak forces separated. Each separation released energy, potentially driving the universe's expansion. And then came inflation. Before we reach inflation, we must linger in the quantum era, the earliest moments of the universe where our most fundamental theories collide and break down. This epoch, lasting from time 0 to about 10⁻43 seconds, the Planck time, represents the frontier of human knowledge about reality itself. At the Planck scale, distances become so small, about 10⁻35 meters, that the smooth fabric of space-time, described by general relativity, gives way to quantum foam. Imagine zooming into empty space with an impossibly powerful microscope. At everyday scales, space looks smooth and continuous. At atomic scales, it still appears smooth. But at the Planck scale, space itself becomes turbulent, foamy, fluctuating wildly. In this quantum foam, tiny wormholes might pop in and out of existence. Virtual black holes could form and evaporate in instants too brief to measure. Space might have extra dimensions, curled up so small they're invisible. The distinction between space and time might blur or vanish entirely. This is the realm where we need quantum gravity, a theory that merges quantum mechanics with general relativity. We don't have such a theory yet, though candidates exist. String theory proposes that fundamental particles are actually tiny vibrating strings of energy. Different vibration patterns produce different particles. An electron is a string vibrating one way, a quark another way, a photon yet another. String theory naturally incorporates gravity and suggests extra spatial dimensions beyond the three we experience. In string theory, the universe might have begun as a collision between higher dimensional objects called branes. Our three-dimensional space could be a brane floating in a higher dimensional space called the bulk. The Big Bang might have been two branes colliding, releasing energy that became our universe. Loop quantum gravity takes a different approach. Rather than adding extra dimensions or new fundamental objects, it quantizes space-time itself. Space is not continuous, but made of tiny discrete units, quanta of area and volume. The smallest possible area is about 1 Planck length squared. You can't subdivide space infinitely. It has a fundamental graininess. Imagine space as a fabric. At everyday scales, the fabric appears smooth and continuous. But zoom in far enough, and you see the individual threads, the quanta of space. These threads weave together to create the smooth space-time we experience. The mathematics of loop quantum gravity describes how these quantum threads connect and interact. In loop quantum gravity, the Big Bang singularity might be resolved. Instead of infinite density, the universe reaches a maximum finite density, then bounces. The Big Bang becomes a big bounce, the transition from a previous contracting phase to our current expanding phase. The universe might be eternal, oscillating between expansion and contraction. This bounce scenario has profound implications. If our Big Bang was a bounce, then our universe has a prehistory. Before the bounce, a previous universe existed, contracting toward the big crunch that became our Big Bang. That previous universe might have had different properties, different galaxy distributions, different histories, but the same underlying physics. Some cosmologists have tried to find observational signatures of a pre-bounce universe. Certain patterns in the cosmic microwave background might encode information from before the bounce. So far, no definitive evidence has emerged, but the search continues. Causal set theory proposes that space-time is fundamentally discrete, not a smooth continuum but a collection of discrete events connected by causal relationships. The apparent smoothness of space-time emerges from the collective behavior of countless tiny events, like how water appears continuous even though it's made of molecules. Each of these theories makes different predictions about what happened at the very beginning. Unfortunately, these predictions are extraordinarily difficult to test. The energies involved, the Planck energy, are about 1 trillion times higher than our most powerful particle accelerators can achieve. We may never directly probe Planck scale physics, but there are indirect signatures we might detect. Quantum gravity effects could leave subtle imprints on the cosmic microwave background. Some theories predict slight deviations from perfect scale, invariance in the primordial fluctuations. Others predict specific patterns in gravitational waves from inflation. The search continues. Each new observation of the early universe, every precision measurement of the CMB, every detection of primordial gravitational waves constrains these theories, ruling some out and supporting others. One profound implication of quantum cosmology is that the universe might have created itself. In quantum mechanics, particles can tunnel through barriers they classically couldn't cross. Could the universe have tunneled into existence from nothing? Stephen Hawking and James Hartle proposed the no-boundary proposal. In this model, the universe has no beginning in the usual sense. As you trace time backward, approaching the Big Bang, time gradually transforms into a space-like dimension. The universe's beginning is smooth and finite, like the South Pole on Earth, not an edge or boundary, just a smooth point where all directions lead north, or in this case, forward in time. Alexander Vilenkin proposed a different model, quantum tunneling from nothing. In this scenario, the universe spontaneously appeared from literally nothing, no space, no time, no matter, no energy, no quantum vacuum, through a quantum fluctuation. The probability of such an event is extraordinarily small. But if nothing exists, even tiny probabilities can be realized because there's no time for them not to occur. These ideas remain speculative, but they illustrate how profoundly quantum mechanics might reshape our understanding of cosmic origins. The quantum era also raises questions about the nature of time itself. In everyday physics, time flows in one direction, the arrow of time. Entropy increases. Eggs break, but don't unbreak. We remember the past, but not the future. But the fundamental laws of physics are mostly time-symmetric. A movie of two particles colliding looks the same whether played forward or backward. The arrow of time emerges from statistics and initial conditions, not fundamental physics. At the Big Bang, entropy was extremely low. The universe was in a highly ordered, uniform state. The subsequent increase in entropy gives time its direction. But why was the early universe so ordered? This is the past hypothesis, and it remains mysterious. Some physicists speculate that at the quantum era, before entropy had meaning, there was no arrow of time. Past and future were indistinguishable. The emergence of time's arrow might have been part of how the universe crystallized from quantum chaos into classical space-time. These are deep waters, and we're far from shore, but they hint at the profound transformations our understanding of reality might undergo as we probe ever closer to the beginning. For now, let's proceed to firmer ground to inflation, about 10⁻36 seconds after the Big Bang, where our theories become more reliable and our predictions more testable. Inflation is one of the most radical and important concepts in modern cosmology. It proposes that for a tiny fraction of a second, from about 10⁻36 to 10⁻32 seconds after the Big Bang, the universe expanded exponentially, doubling in size every 10⁻37 seconds or so. In that brief instant, the universe grew by a factor of at least 10, 26, possibly much more. A region smaller than a proton expanded to the size of a marble, then a basketball, then larger than the observable universe today, all in less than a trillionth of a second. This sounds impossible. How can anything expand faster than light? Doesn't relativity forbid that? The key is that relativity forbids objects from moving through space faster than light. But space itself can expand at any rate. During inflation, space expanded faster than light could traverse it, but no object moved through space at superluminal speeds. Why did inflation happen? The leading theory involves a hypothetical field called the inflaton field. Just as electromagnetic fields permeate space, the inflaton field filled the early universe. This field had a peculiar property. It created negative pressure or tension, which caused space to expand exponentially. Think of it like a stretched rubber sheet. Normal matter creates positive pressure, pulling things together through gravity. But the inflaton field had negative pressure, pushing space apart. The more space expanded, the more inflaton field there was, creating more negative pressure and accelerating the expansion, a runaway feedback loop. Eventually, the inflaton field decayed, releasing its energy into ordinary matter and radiation. This process, called reheating, ended inflation and filled the universe with the hot plasma that would evolve into stars, galaxies, and everything else. The reheating process was violent and complex, as the inflaton field oscillated around the minimum of its potential energy. It coupled to other fields, creating particles. These particles collided and interacted, thermalizing into a hot plasma. The temperature after reheating could have been as high as 1027 Kelvin, hot enough to create the heaviest particles physics allows. Reheating set the initial conditions for the hot Big Bang that followed. Everything we've discussed about particle physics in the early universe, the quark-gluon plasma, the formation of protons and neutrons, nucleosynthesis, all occurred after reheating in the hot universe created by inflation's end. The energy scale of inflation is one of its key unknowns. Different models predict different energy scales, ranging from about 10-16 GeV, near the scale of grand unified theories, down to much lower values. The energy scale determines the amplitude of gravitational waves produced during inflation, which in turn affects the polarization of the CMB. Detecting or ruling out these gravitational waves would nail down the energy scale and discriminate between inflation models. Inflation solves several puzzles about the universe. The horizon problem. Different regions of the universe have almost exactly the same temperature, even though they're so far apart they couldn't have communicated since the Big Bang. How did they coordinate to be the same temperature? Inflation solves this. Before inflation, these regions were close enough to equalize their temperatures. Inflation then stretched them to vast distances while preserving their uniformity. The flatness problem. The universe appears geometrically flat. Parallel lines stay parallel. The angles of triangles add to 180 degrees. But general relativity says space should be curved by matter and energy. Maintaining flatness requires a precise balance between expansion rate and density. How did the universe achieve this balance? Inflation solves this. Exponential expansion stretches any curvature flat, like inflating a balloon makes its surface appear flat locally. The monopole problem. Grand unified theories predict that magnetic monopoles isolated north or south poles should have formed in the early universe in huge numbers. We've never found one. Inflation solves this. Monopoles formed before inflation then were diluted to near nothingness when the universe expanded exponentially. But inflation does more than solve problems. It makes predictions, and these predictions have been confirmed. Inflation predicts that quantum fluctuations in the inflaton field would be stretched to cosmic scales, creating tiny density variations across the universe. Regions that were slightly denser would eventually attract more matter through gravity, forming the seeds of galaxies and galaxy clusters. These density variations should appear as temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang. And they do. Satellites like COBE, WMAP, and Planck have measured these fluctuations with extraordinary precision. The pattern matches inflation's predictions remarkably well. Inflation also predicts gravitational waves ripples in spacetime generated during the exponential expansion. These primordial gravitational waves should leave a subtle imprint on the cosmic microwave background. Detecting this imprint would be smoking gun evidence for inflation. In 2014, the BICEP 2 experiment announced the detection of this signature, causing enormous excitement. But further analysis showed the signal was probably from dust in our galaxy, not primordial gravitational waves. The search continues, but if found, it would confirm inflation and tell us the energy scale at which it occurred. Despite its successes, inflation isn't without problems. We don't know what the inflaton field is. No known particle or field matches its properties. It might be related to the Higgs field, or dark energy, or something entirely new. There's also the fine-tuning problem. Inflation requires very specific initial conditions. The inflaton field must start with just the right energy in just the right state. How did these conditions arise? Some theorists argue this is just pushing the mystery back one step, explaining one fine-tuning by invoking another. Eternal inflation, mentioned earlier, suggests that inflation never truly ends globally. In most regions, inflation continues forever, but quantum fluctuations occasionally cause the inflaton field to decay locally, creating bubbles where inflation stops. Our universe is one such bubble. If eternal inflation is correct, there are infinite bubble universes, each with potentially different physical laws and constants. We live in a universe with laws that permit life because, in an infinite multiverse, all possible conditions occur somewhere, and observers only exist where conditions are right. This multiverse concept is controversial. Critics argue it's untestable and therefore not science. Proponents respond that it's a prediction of our best theories, and while individual universes might be unobservable, the theory as a whole makes testable predictions about our universe. Regardless of these debates, inflation remains the best explanation we have for the universe's large-scale properties. It transformed cosmology from a speculative field to a precision science where theoretical predictions match observations to exquisite accuracy. And inflation set the stage for everything that followed. When it ended, the universe was a hot, dense, expanding plasma filled with energy that would soon condense into matter. The first particles were about to form. After inflation ended, about 10-32 seconds after the Big Bang, the universe was incredibly hot around 1027 Kelvin and filled with pure energy. No stable particles existed yet. Temperature was far too high for anything we'd recognize as matter. Energy and matter are interchangeable. Einstein's famous equation tells us this. At high temperatures, energy spontaneously converts to particle-antiparticle pairs, and these pairs annihilate back into energy. A seething, chaotic dance of creation and destruction filled the cosmos. As the universe expanded, it cooled. And as it cooled, particles began to stabilize. First to form were quarks and gluons, the fundamental building blocks of protons and neutrons. Quarks come in 6 types or flavors: up, down, charm, strange, top, and bottom. Gluons are the particles that carry the strong nuclear force binding quarks together. At this stage, called the quark epoch, quarks and gluons existed freely in a hot quark-gluon plasma. They couldn't bind into protons and neutrons, yet temperature was too high, and collisions kept breaking any bonds that formed. Alongside quarks, leptons appeared. Leptons are another family of fundamental particles, including electrons and neutrinos. Neutrinos are ghostly particles that barely interact with matter, passing through solid objects as if they weren't there. Trillions of neutrinos pass through your body every second, left over from the Big Bang. All these particles had antimatter counterparts, antiquarks, antileptons. When matter meets antimatter, both annihilate, converting their mass into energy. So why is the universe made of matter, not antimatter? Why didn't everything annihilate? This is the mystery of matter-antimatter asymmetry. For every billion particle-antiparticle pairs, there was one extra matter particle, a tiny imbalance, but crucial. When annihilation finished, that tiny excess remained, becoming all the matter in the universe today. We don't fully understand why this asymmetry exists. It's one of cosmology's major unsolved problems. Slight differences in how matter and antimatter interact, CP violation might explain it, but current theories don't quite account for the observed asymmetry. It might involve physics beyond the standard model, possibly connected to neutrinos or exotic particles we haven't discovered. The standard model of particle physics does include CP violation processes where matter and antimatter behave differently. This was discovered in the decay of kaon particles in 1964 and later confirmed in B mesons and other particles. But the amount of CP violation in the standard model is far too small to explain the observed matter-antimatter asymmetry. Something must have happened in the early universe, some process involving physics we don't yet understand that preferentially created matter over antimatter. This process must have satisfied three conditions, known as the Sakharov conditions: violation of baryon number, the total count of matter particles, CP violation, and departure from thermal equilibrium. Several mechanisms have been proposed. Leptogenesis suggests that the asymmetry first appeared in neutrinos, then was converted to an asymmetry in protons and neutrons through processes in the early universe. Electroweak baryogenesis proposes that the asymmetry was created during the electroweak phase transition, when the electromagnetic and weak forces separated. Afflectine baryogenesis invokes supersymmetric particles to generate the asymmetry. None of these mechanisms has been confirmed. The origin of matter remains one of the deepest puzzles in physics. We exist because of a tiny imbalance we don't understand, a humbling reminder of how much we still have to learn. About 10⁻⁶ seconds, 1 microsecond, after the Big Bang, the universe cooled to about 13 Kelvin cooler, but still trillions of degrees. At this temperature, quarks could finally bind together. 3 quarks combine to make baryons, protons, and neutrons. 2 quarks make mesons. This transition, called the quark-hadron transition or QCD phase transition. QCD stands for quantum chromodynamics, the theory of the strong force, was like a phase change, similar to water freezing into ice. Before, free quarks and gluons. After, bound hadrons. The quark-gluon plasma condensed into a hadron gas. Most hadrons are unstable and decay quickly, but protons and neutrons are stable, or nearly so. Free neutrons decay in about 15 minutes, but protons are stable indefinitely, as far as we know. These became the building blocks of atomic nuclei. At this point, the universe was a hot soup of protons, neutrons, electrons, neutrinos, and photons, particles of light, all zipping around at nearly the speed of light, constantly colliding. About 1 second after the Big Bang, the 1 second mark is significant because it's the first time we can describe with complete confidence. Before this, conditions were more extreme and uncertain. The universe had cooled to about 10 Kelvin, around 1 billion degrees. Neutrinos stopped interacting with other particles. They became so weakly interacting that they essentially froze out, no longer colliding with anything. These neutrinos are still around today, forming a cosmic neutrino background analogous to the cosmic microwave background. We haven't detected them yet. They're even more elusive than cosmic microwave photons, but we're confident they exist. Now we come to Big Bang nucleosynthesis, one of the great triumphs of cosmology. Let us pause and appreciate the remarkable drama of the first seconds after the Big Bang. In this brief window, shorter than a heartbeat in cosmic terms, the universe underwent more radical transformations than it would experience in the next 13.8 billion years combined. At 1/10 of a second after the Big Bang, the temperature was still about 30 billion degrees Kelvin. Electrons and positrons, anti-electrons, existed in vast numbers, constantly creating and annihilating in pairs. The universe was opaque, a dense fog of particles and radiation. Light could travel only a tiny distance before scattering off something. The particle physics at this epoch was remarkably complex. Photons, particles of light, outnumbered matter particles by about 1 billion to 1. These photons were incredibly energetic, gamma rays with enough punch to create particle-antiparticle pairs. The universe was a seething cauldron of matter, antimatter, and radiation, all in thermal equilibrium. Muons and tau leptons, heavier cousins of the electron, had already annihilated by this point. They're unstable and decay quickly. At earlier times, when temperatures were higher, they existed in abundance, but by 1/10 of a second, only electrons and their antiparticles remained among the charged leptons. Neutrinos, those ghostly particles, swarmed through the plasma. 3 types of neutrinos exist: electron neutrinos, muon neutrinos, and tau neutrinos. All were present in enormous numbers, interacting weakly with the other particles. The weak nuclear force, despite its name, was still strong enough at these temperatures to keep neutrinos in thermal equilibrium with everything else. At this moment, the universe contained roughly equal numbers of protons and neutrons, maintained by the weak nuclear force. Reactions converted protons to neutrons and vice versa, keeping them in equilibrium. The slight mass difference between protons and neutrons are about 0.1% heavier, meant that neutrons were slightly less favored as temperatures dropped. At 1 second, the universe cooled to about 10 billion degrees. The weak interactions that converted protons to neutrons became too slow to keep up with the expansion. The proton-to-neutron ratio froze at about 7:1. This ratio would determine how much helium the universe could make. Also, at 1 second, neutrinos decoupled from the rest of matter. They stopped interacting and began their long, lonely journey through the universe. These primordial neutrinos, cooled by expansion to just 1.9 Kelvin today, form an invisible background that permeates all of space. Detecting this cosmic neutrino background is one of cosmology's great challenges and potential triumphs. Between 1 and 10 seconds, electron-positron annihilation peaked, As the universe cooled below about 5 billion degrees, it could no longer create new electron-positron pairs from radiation. The existing pairs annihilated, converting their mass into photons. For every billion electron-positron pairs, there was one extra electron corresponding to the matter-antimatter asymmetry we mentioned. These excess electrons survived and eventually paired with protons to make hydrogen atoms. The annihilation heated the photons relative to the neutrinos, which had already decoupled and couldn't share this energy. This is why the cosmic neutrino background is cooler than the cosmic microwave background. The neutrinos missed the energy boost from electron-positron annihilation. At 10 seconds, the universe was about 3 billion degrees. Conditions were approaching those needed for nuclear fusion, but not quite there yet. Free neutrons were starting to decay, converting to protons with a half-life of about 15 minutes. The clock was ticking. If fusion didn't begin soon, too many neutrons would decay and very little helium could form. At 3 minutes, fusion finally began. The temperature dropped to about 1 billion degrees, cool enough for deuterium, a proton, plus a neutron, to survive without being immediately shattered by energetic photons. This moment, called the deuterium bottleneck, opened the floodgates to nucleosynthesis. Once deuterium could form, a rapid chain of reactions built heavier nuclei. Deuterium plus a neutron makes tritium. Deuterium plus a proton makes helium-3. Tritium plus a proton, or helium-3 plus a neutron, makes helium-4. Within about 17 minutes, nearly all the neutrons had been incorporated into helium nuclei. The final composition, about 75% hydrogen by mass, 25% helium-4, with traces of deuterium, about 0.01%, helium-3, and lithium-7. This primordial composition is observed in the oldest, most pristine gas clouds and matches Big Bang predictions beautifully. After 20 minutes, the nuclear furnace shut down. The universe had expanded and cooled too much for fusion to continue. Heavy elements, carbon, oxygen, iron, would have to wait for stars hundreds of millions of years in the future. For the next 380,000 years, the universe remained a hot plasma. Nuclei existed, but electrons were too energetic to bind to them. Photons bounced constantly off free electrons, making the universe opaque. No light could travel far. This period is sometimes called the thermal history of the universe. Nothing dramatic happened, just slow cooling, gradual expansion, and the inexorable dilution of matter and radiation. But this apparent stasis set the stage for the next great transformation, the formation of atoms and the release of light. Between about 1 second and 20 minutes after the Big Bang, the universe was a nuclear reactor, fusing light elements from protons and neutrons. This era, called Big Bang nucleosynthesis, BBN, created most of the helium and trace amounts of lithium and beryllium in the universe. At the 1 second mark, temperature was still around 10 Kelvin. Protons and neutrons were in thermal equilibrium, interconverting through weak interactions. Neutrons could turn into protons by emitting electrons and neutrinos. Protons could turn into neutrons by capturing electrons or positrons. The ratio of neutrons to protons was determined by their relative masses and the temperature. As the universe expanded and cooled, these interactions slowed. Around 1 second, they effectively stopped. Neutrons and protons froze out at a ratio of about 1 neutron for every 7 protons. But free neutrons are unstable. They decay with a half-life of about 15 minutes. As the universe continued cooling, neutrons began decaying into protons. After a few minutes, only about 1 neutron remained. For every 7 protons, this ratio would determine how much helium formed. About 3 minutes after the Big Bang, temperature dropped to about 10.9 Kelvin, around 1 billion degrees, cool enough for nuclear fusion to occur without immediately being disrupted by collisions. Fusion began. Protons and neutrons combined into deuterium-heavy hydrogen with 1 proton and 1 neutron. Deuterium nuclei fused to form helium, 2 protons, 1 neutron, and helium-4 2 protons, 2 neutrons. Tiny amounts of lithium-7 also formed. Why did fusion stop with helium and lithium? Why not continue to carbon, oxygen, and heavier elements? 2 reasons. First, the universe was expanding and cooling rapidly. Within about 20 minutes, temperature dropped below the threshold for fusion. Second, there's no stable nucleus with 5 protons and neutrons. Fusion naturally stops at helium-4, mass number 4, because the next step, adding another nucleon to make mass 5, produces unstable nuclei that immediately decay. Jumping to mass 6, lithium requires a rare 3-body collision, so very little lithium forms. Heavy elements would have to wait for stars. When BBN ended, about 25% of the universe's mass was in helium-4, about 75% was still hydrogen, single protons, and trace amounts were deuterium, helium-3, and lithium-7. This prediction, 25% helium, 75% hydrogen, is one of the Big Bang theory's most successful. When we measure the helium abundance in the oldest stars and gas clouds, we find 25% helium, 75% hydrogen. The match is extraordinary, confirming that the Big Bang model correctly describes the universe a few minutes after creation. Moreover, the precise abundances of deuterium, helium-3, and lithium depend on the density of ordinary matter in the universe. By measuring these abundances and comparing to BBN predictions, we can determine how much ordinary matter exists, and it matches independent measurements from the cosmic microwave background. Everything fits together beautifully. But there's one puzzle, the lithium-7 problem. The observed abundance of lithium 7 inches old stars is lower than BBN predicts by a factor of 3. We don't know why. Maybe lithium was destroyed in stars more than we thought. Maybe our nuclear physics isn't quite right. Or maybe it's a clue to new physics. It's a small discrepancy, but it's puzzling. After BBN, the universe was still too hot for atoms. Nuclei existed, but electrons were unbound, zipping freely through space. The universe was a plasma, a hot gas of charged particles opaque to light because photons constantly scattered off free electrons. For the next 380,000 years, not much happened. The universe expanded and cooled, but no new structures formed. This is sometimes called the boring era, or the dark ages of the Big Bang, though technically the dark ages come later. Gradually, temperature dropped. The plasma cooled, and eventually it reached a critical threshold, 3000 Kelvin, cool enough for electrons to bind to nuclei, forming neutral atoms. This moment changed everything. About 380,000 years after the Big Bang, the universe cooled to approximately 3000 Kelvin, around the temperature of a hot stove element. At this temperature, electrons could finally bind to hydrogen and helium nuclei without being immediately knocked free by collisions. This transition, called recombination, a misnomer since the electrons were never combined before, but the name stuck, was like a cosmic sunrise. As atoms formed, the universe became transparent to light. Recombination didn't happen instantaneously. It was a gradual process lasting about 100,000 years. As the universe cooled through the critical temperature range, more and more electrons found their way into atomic orbitals. The fraction of neutral atoms increased steadily until, eventually, almost all the hydrogen and helium in the universe was neutral. The physics of recombination is subtle. You might expect atoms to form when the temperature drops below the ionization energy of hydrogen, about 13.6 electron volts, corresponding to about 158,000 Kelvin. But recombination actually occurred at much lower temperatures, around 3000 Kelvin. Why the difference? Because photons vastly outnumbered atoms. Even at temperatures well below the ionization energy, there were enough high-energy photons in the tail of the thermal distribution to ionize any atoms that tried to form. Only when the temperature dropped low enough that even these rare high-energy photons became scarce could atoms persist. This is an example of a Saha equilibrium. The balance between ionization and recombination depends not just on temperature but also on the ratio of photons to atoms. In the early universe, with 1 billion photons for every atom, recombination was delayed until much lower temperatures. Before recombination, photons constantly scattered off free electrons, unable to travel far, like trying to see through fog. After recombination, photons could travel freely through space, no longer blocked by free electrons like fog lifting, revealing a clear view. The photons that were released at recombination are still traveling through the universe today. We see them as the cosmic microwave background, CMB, a faint glow of radiation coming from all directions in space. When the CMB was emitted, the radiation was visible light, glowing orange-red like a hot ember. But 13.8 billion years of cosmic expansion has stretched those photons' wavelengths, redshifting them from visible to microwave about 1 millimeter wavelength, the same as inside a microwave oven. The CMB's temperature today is 2.7 Kelvin, just above absolute zero. This is the cooled down radiation from a 3000 Kelvin plasma, redshifted by a factor of about 1100 due to the universe's expansion. The CMB was discovered accidentally in 1964 by Arno Penzias and Robert Wilson, two engineers at Bell Labs, testing a radio antenna. They found a persistent noise coming from all directions, which they initially thought was interference, maybe pigeon droppings on the antenna. After cleaning the antenna and eliminating all possible sources of error, the signal remained. They discovered the CMB, the echo of the Big Bang. This discovery earned them the Nobel Prize and provided powerful confirmation of the Big Bang theory. The universe really did have a hot, dense beginning. But the CMB is more than just confirmation, it's a treasure trove of information about the early universe. The CMB is almost perfectly uniform, the same temperature in every direction to within 1 part in 100,000. This uniformity supports inflation. The universe was smoothed by exponential expansion, erasing any initial irregularities. But almost uniform is key. There are tiny temperature variations about 0.00001 Kelvin across the sky. These fluctuations are the seeds of all structure in the universe. Slightly hotter spots correspond to regions that were slightly denser at recombination. Gravity pulled matter into these denser regions, amplifying the density contrast. Over hundreds of millions of years, these density enhancements grew, eventually collapsing into the first stars and galaxies. Cooler spots were slightly less dense, eventually becoming voids, the vast empty regions between galaxy clusters. The CMB's temperature fluctuations thus encode the initial conditions for structure formation. By measuring them precisely, we can test theories of the early universe and determine cosmic properties. Several space missions have mapped the CMB with increasing precision. COBE Cosmic Background Explorer, launched in 1989, first detected the CMB's temperature fluctuations, earning its team the Nobel Prize. COBE's resolution was coarse. It saw large-scale patterns but not fine details. WMAP Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped the CMB with much higher resolution and sensitivity. WMAP's data revolutionized cosmology, precisely measuring the universe's age, 13.8 billion years. Composition 5% ordinary matter, 27% dark matter, 68% dark energy, and geometry flat. Planck, launched in 2009, provided the most detailed CMB map to date. Planck's measurements are so precise that they've detected subtle effects like gravitational lensing of the CMB by intervening matter and the influence of the universe's first generation of stars. The precision of these measurements is staggering. Planck measured the CMB temperature to within a few millionths of a degree. It detected temperature fluctuations as small as 10 millionths of a degree. From these tiny variations, cosmologists extracted values for fundamental cosmic parameters with uncertainties of just a few percent. Consider what this means. By measuring the temperature of ancient light from 13.8 billion years ago, we can determine the age of the universe, 13.8 billion years, give or take 40 million. The curvature of space, flat to within 0.4%. The amount of ordinary matter, 4.9%, dark matter, 26.8%, and dark energy, 68.3%. We can determine when the first stars formed, how the universe expanded over time, and the initial conditions from which all structure grew. The CMB also contains polarization, a subtle orientation in the electromagnetic waves. This polarization encodes additional information about the early universe, including hints about inflation. The BICEP Keck experiments at the South Pole search for a specific polarization pattern called B-modes, which would be smoking gun evidence for gravitational waves from inflation. Future missions aim to measure the CMB with even greater precision. The Simons Observatory, under construction in Chile's Atacama Desert, will map CMB polarization with unprecedented sensitivity. Lightbird, a planned Japanese space mission, will search for primordial gravitational wave signatures. These observations might reveal whether inflation happened, at what energy scale, and possibly even detect signatures of quantum gravity. These CMB observations have confirmed cosmology's predictions with stunning accuracy. The observed fluctuations match inflation's predictions almost exactly. The statistical distribution of hot and cold spots, their sizes, and their correlations all fit the theory beautifully. The CMB also carries information about the universe's composition. The pattern of fluctuations depends on several factors: how much ordinary matter exists, how much dark matter, the expansion rate, and the geometry of space. By fitting theoretical models to the data, cosmologists extract these parameters. The result: ordinary matter, protons, neutrons, electrons, makes up only 5% of the universe's total energy. dark matter contributes 27%. Dark energy, a mysterious force accelerating the universe's expansion, comprises 68%. This composition, determined from the CMB, matches independent measurements from galaxy surveys and supernova observations, confirming we understand the universe's broad strokes. The CMB even gives hints about inflation. The spectrum of fluctuations, how temperature variations depend on angular scale, is nearly scale invariant, meaning fluctuations at all sizes have roughly the same amplitude. This scale invariance is a generic prediction of inflation, and the CMB confirms it. However, there are anomalies, small deviations from the simplest models. The fluctuations at the largest scales, covering a significant fraction of the sky, are slightly weaker than expected. There's a hint of a preferred direction, violating the expected isotropy. These anomalies might be statistical flukes, or systematic errors, or clues to new physics. More data is needed. The CMB also marks the beginning of the cosmic dark ages, not a misnomer this time. After recombination, the universe was dark. Stars hadn't formed yet. The only light was the fading afterglow of the Big Bang, redshifting into invisibility. For hundreds of millions of years, the universe was dark and cold, filled with neutral hydrogen and helium, waiting for the first stars to ignite. But those stars were coming. Gravity was already pulling matter together, building the structures that would light up the cosmos. After recombination, the universe entered a phase aptly named the Cosmic Dark Ages. For hundreds of millions of years, from about 380,000 to roughly 100 to 200 million years after the Big Bang, the universe contained no luminous objects. No stars, no galaxies, no quasars. Just neutral hydrogen and helium gas, slowly clumping under gravity. Why couldn't stars form immediately? Several reasons. First, the gas was still very hot from the Big Bang, thousands of Kelvin. Gas needs to cool to condense under its own gravity. Cooling takes time. Second, the gas was incredibly uniform, with density variations of only 1 part in 100,000. Gravity needs contrast denser regions to pull matter from less dense surroundings. Building up significant overdensities from such tiny seeds required time. Third, the gas had momentum. Everything was expanding with the Hubble flow. To collapse and form structures, gravity had to overcome this expansion, pulling matter together against cosmic expansion. This happened gradually, starting with the most overdense regions. Dark matter played a crucial role. Unlike ordinary matter, dark matter doesn't interact with light or feel electromagnetic forces, it only responds to gravity. This meant dark matter could clump freely, unimpeded by radiation pressure or other forces that affect ordinary matter. Dark matter began collapsing into gravitational wells, called dark matter halos, immediately after recombination. Possibly even before. These halos grew denser, and their gravity pulled ordinary matter inward. Gas fell into the dark matter halos, pooling at the center, eventually becoming dense and cool enough to form stars. Without dark matter, structure formation would have been much slower. Ordinary matter, affected by radiation pressure during recombination, was delayed in collapsing. Dark matter provided the gravitational scaffolding, allowing structure to form much faster than it could from ordinary matter alone. Computer simulations of structure formation, called N-body simulations, model millions or billions of dark matter particles following their gravitational interactions over cosmic time. These simulations reveal a cosmic web structure. Dark matter forms filaments and sheets, with dense nodes where filaments intersect. Galaxies form at these nodes. The structure resembles neural networks or spider webs, a beautiful organic-looking pattern emerging from simple gravitational physics. Observations confirm this. Modern galaxy surveys map millions of galaxies across vast volumes of space. The distribution shows exactly this cosmic web pattern. Galaxies line up along filaments, surrounding vast voids. The match between simulations and observations is striking, validating our understanding of structure formation. But while dark matter sets the stage, ordinary matter makes stars, and stars changed everything. The first dark matter halos formed at around 100 million years after the Big Bang, with masses perhaps 1,000,000 times the Sunday gas, fell into these halos, compressed and heated by the infall. As density increased, so did temperature from gravitational compression. Eventually, at the centers of the most massive halos, temperatures reached millions of degrees, hot enough to ignite nuclear fusion. Hydrogen began fusing into helium. Stars were born. The first generation of stars, called Population 3, were unlike any stars we see today. They were massive, hundreds of times the Sun's mass, and they burned incredibly hot and bright, with surface temperatures over 100,000 Kelvin. The terminology of stellar populations comes from the history of astronomy. When astronomers first classified stars by their metal content, remember, in astronomy, metals means anything heavier than helium. They called metal-rich stars like our Sun Population I, and metal-poor old stars Population 2. When they realized there must have been even earlier, completely metal-free stars, those were dubbed Population 3, even though they came first chronologically. Population 3 stars faced a unique challenge: how to form at all. Star formation requires gas clouds to collapse under their own gravity, but collapsing gas heats up. If the gas gets too hot, it expands and stops collapsing. Normal gas clouds cool by radiating energy, and heavy elements like carbon and oxygen are excellent at radiating energy away. But Population 3 stars had no heavy elements. Their gas clouds could only cool through hydrogen and helium, which are much less efficient coolants. This meant the gas stayed hotter, and the minimum mass for a collapsing cloud was much larger. Population 3 stars were necessarily massive. Computer simulations of primordial star formation suggest that individual Population 3 stars might have ranged from about 10 to several hundred solar masses, with typical masses perhaps around 100 solar masses. Some simulations even suggest that the first stars might have formed in small groups or binaries rather than in isolation. Why were they so massive? Because they formed from primordial gas, pure hydrogen and helium from the Big Bang, with no heavier elements. Heavy elements carbon, oxygen, iron are efficient coolants. They radiate energy effectively, allowing gas clouds to cool and fragment into smaller clumps. Smaller clumps make smaller stars. But Population 3 stars had no heavy elements. Those hadn't been created yet. Their gas clouds cooled inefficiently, remaining hotter and more diffuse. Only the most massive clumps could collapse against thermal pressure. Result: very massive stars. These stars lived fast and died young. A star's lifetime depends inversely on its mass. More massive stars burn their fuel much faster. The Sun will live about 10 billion years. A 100 solar mass Population 3 star lived only a few million years, but in those brief lifetimes, they transformed the universe. First, they produced light-intense ultraviolet radiation. This UV radiation ionized surrounding hydrogen, creating bubbles of ionized gas around each star. As more stars formed, these ionized bubbles expanded and merged, gradually reionizing the universe. This epoch of reionization, occurring roughly between 100 million and 1 billion years after the Big Bang, ended the Dark Ages. The universe became ionized again, similar to its state before recombination, but much less dense. This time, the plasma was so diffuse that it remained transparent to most light. Second, population 3 stars created heavy elements. Through nuclear fusion in their cores, they converted hydrogen to helium, helium to carbon and oxygen, and in their final moments, rapid fusion produced elements up to iron. When they died, and they died spectacularly, in supernovae, explosions, or possibly even more exotic hypernovae, they scattered these newly forged elements into space. The surrounding gas became enriched with metals. Astronomers call everything heavier than helium metals, regardless of actual chemistry. This enriched gas formed the next generation of stars, population 2, which had some heavy elements and could be somewhat smaller. Eventually, population 3 stars like our Sun formed, with a substantial fraction of heavy elements, allowing planetary systems and, eventually, life. Population 3 stars were thus the universe's first chemists, creating the periodic table's elements from primordial hydrogen and helium. We've never directly observed a population 3 star, they all died billions of years ago. But we've seen their signatures, the metallicity of ancient stars. The oldest stars we observe, in globular clusters and the Milky Way's halo, have very low heavy element abundances, suggesting they formed from gas only slightly enriched by the first supernovae. Extremely distant galaxies. When we look at galaxies billions of light years away, we see them as they were billions of years ago. The farthest galaxies, seen when the universe was only a few 100 million years old, show spectroscopic signatures consistent with being powered by massive, hot stars, likely including population 3 remnants. The reionization signature in the CMB. The CMB shows subtle evidence of reionization, consistent with the first stars forming and ionizing their surroundings around 100 to 200 million years after the Big Bang. Future telescopes, like the James Webb Space Telescope, JWST, might glimpse population 3 stars directly. JWST, optimized for infrared observations, can peer back to the universe's first few 100 million years, potentially seeing the light from the first stars redshifted into the infrared. As of this writing, JWST has found tantalizing candidates, galaxies, and possibly individual stars from the first billion years, though confirming their nature requires detailed follow-up. Population 3 stars seeded the formation of larger structures. Their supernovae shockwaves compressed surrounding gas, triggering further star formation. Their heavy element enrichment allowed more efficient cooling, producing subsequent generations of smaller, longer-lived stars. Multiple generations of stars formed within the first dark matter halos, building up stellar populations. These became the first galaxies. Galaxies are the building blocks of the visible universe, vast collections of stars, gas, dust, and dark matter bound together by gravity. They range from dwarf galaxies with millions of stars to giant ellipticals with trillions. The first galaxies formed within a few 100 million years after the Big Bang, emerging from the densest dark matter halos where gas had cooled and stars had ignited. The James Webb Space Telescope, JWST, launched in December 2021, has revolutionized our view of these earliest galaxies. JWST's infrared capabilities allow it to peer back to when the universe was only a few 100 million years old, seeing light that has been stretched by cosmic expansion into infrared wavelengths. What JWST has found has surprised astronomers. Galaxies appeared earlier than expected, some within just 300 million years of the Big Bang. These early galaxies are more massive and more luminous than theoretical models predicted. Either galaxies formed more efficiently in the early universe than we thought, or our models of star formation and galaxy assembly need revision. Some of the most distant galaxies JWST has observed have redshifts of 10, 11, even 13 or higher. A redshift of 13 means we're seeing the galaxy as it was when the universe was only about 325 million years old, just 2.4% of its current age. These are among the most distant objects ever observed, and their very existence challenges our understanding of how quickly structure formed. These early galaxies were small, irregular, chaotic clumps of a few million to a billion stars, undergoing intense bursts of star formation. Nothing like the grand spiral or elliptical galaxies we see today, but they were important. Through a process called hierarchical merging, small galaxies collided and merged into larger ones, gradually building the massive galaxies we observe. Imagine two small galaxies, each a few hundred light-years across, colliding over tens of millions of years. Their stars rarely collide. Space within galaxies is mostly empty, but their gas clouds crash together, compressing and heating. This triggers bursts of new star formation. Shockwaves from supernovae drive gas out of the merged galaxy, enriching the surrounding intergalactic medium with metals. Over time, through countless such mergers, galaxies grow. The Milky Way itself likely formed through the merger of dozens or hundreds of smaller galaxies over billions of years. We can see evidence: tidal streams, ribbons of stars torn from smaller galaxies as their absorbed wrap around our galaxy. Globular clusters, ancient, dense star clusters, are remnants of long-gone galaxies. The universe's large-scale structure grew through this same hierarchical process. Small dark matter halos merged into larger ones. Gas funneled along filaments toward dense nodes. Galaxies formed in clusters, which themselves formed superclusters, the largest gravitationally bound structures in the universe, hundreds of millions of light-years across. But galaxies aren't just collections of stars. At their centers lurk supermassive black holes. Almost every large galaxy hosts a supermassive black hole at its core, millions to billions of times the Sun's mass. The Milky Way's central black hole, Sagittarius A*, is about 4 million solar masses. M87, a giant elliptical galaxy, has a black hole 7 billion solar masses. How did these monsters form? We don't fully know, especially how they grew so large so quickly. The most distant quasars, extremely bright galactic cores powered by supermassive black holes, existed when the universe was less than 1 billion years old. How did black holes grow to billions of solar masses in such a short time? Possible mechanisms: direct collapse. Instead of forming stars, some gas clouds collapsed directly into massive black holes, thousands to hundreds of thousands of solar masses, which then grew by accreting gas. Population 3 remnants. The most massive population 3 stars might have left behind large black holes when they died, providing seeds that grew over time. Runaway stellar mergers. In dense star clusters, stars collide and merge, building up a massive central star that collapses into a black hole. Likely, all these processes contributed, with different galaxies forming their central black holes through different paths. As black holes accrete gas, they release enormous energy gas spiraling into a black hole heats to millions of degrees, radiating across the spectrum from radio to X-rays. This emission can outshine the entire galaxy, creating a quasar. Quasars were common in the early universe. Most supermassive black holes were actively feeding, surrounded by abundant gas. Today, quasars are rare. Most supermassive black holes, including our galaxies, are quiescent, having exhausted their nearby fuel. But their past activity shaped galaxies. Energetic outflows from accreting black holes, winds and jets blow gas out of galaxies, suppressing star formation. This feedback regulates galaxy growth, preventing them from forming stars indefinitely. Remarkably, the mass of a galaxy's central black hole correlates with properties of the galaxy's bulge, the central, spherical component. This suggests black holes and galaxies co-evolve, influencing each other's development through feedback mechanisms. As galaxies formed and evolved, the universe's overall star formation rate increased, peaking around 10 billion years ago, about 3 to 4 billion years after the Big Bang. At this cosmic noon, galaxies were forming stars 10 times faster than today. It was the universe's most active, vibrant epoch. Cosmic noon was a time of furious activity. Galaxies collided frequently, their gas clouds compressing and igniting with new stars. Supermassive black holes grew rapidly, feeding on abundant gas and shining as brilliant quasars. Heavy elements accumulated in stellar interiors and spread through interstellar space via stellar winds and supernova explosions. The universe at cosmic noon looked very different from today. Galaxies were smaller, more irregular, more chaotic. Star-forming regions blazed with ultraviolet light. Dust, created by dying stars, began to obscure some of this light, glowing red in the infrared. The cosmic web was denser, with filaments more crowded with matter flowing toward growing galaxies. Since then, star formation has declined. Galaxies have exhausted much of their gas. The universe's expansion has slowed the infall of fresh fuel. Today, star formation is a shadow of its former glory. Our Milky Way forms about 1 solar mass of stars per year, compared to hundreds or thousands in the early universe's most active galaxies. But star formation hasn't ceased. In spirals like the Milky Way, gas continues cycling through. Stars form, live, die, return material to the interstellar medium, and new stars form from that enriched gas. This recycling process continues, albeit slowly, sustaining star formation for billions more years. Elliptical galaxies, in contrast, have little gas and minimal star formation. They're red and dead, populated by old red stars, with few young blue ones. Most ellipticals formed through major mergers that compressed gas, triggering intense star formation bursts that exhausted the fuel. Let us step back and appreciate the universe's grand architecture. The cosmic web is one of the most stunning discoveries of modern cosmology, a vast network of structures spanning billions of light years, organized into a pattern of filaments, sheets, nodes, and voids. Imagine floating in space, far above any individual galaxy. From this vantage point, Galaxies appear not randomly scattered but organized into patterns. They cluster along long, thin filaments, rivers of galaxies flowing through the cosmos. These filaments connect at nodes, dense regions where many filaments intersect. The nodes contain galaxy clusters, the largest gravitationally bound structures in the universe. Between the filaments lie voids, vast, nearly empty regions spanning hundreds of millions of light years. Voids contain few galaxies, just the cosmic background of dark matter and sparse gas. They are the universe's great deserts. Some filaments are truly enormous. The Hercules Corona Borealis Great Wall, discovered in 2013, stretches about 10 billion light-years, the largest known structure in the observable universe. The Sloan Great Wall, at 1.4 billion light-years, was the previous record holder. How did this structure form? From the tiny density fluctuations imprinted during inflation, amplified by gravity over billions of years. In the early universe, regions that were slightly denser than average began attracting surrounding matter. As matter flowed toward these overdense regions, it didn't flow uniformly from all directions. Instead, it flowed along paths of least resistance, creating streams that eventually became filaments. Think of water flowing down a hillside. It doesn't flow uniformly but channels into streams. Streams merge into rivers. Rivers flow into lakes or seas. Similarly, matter in the early universe channeled into filaments that flowed toward dense nodes. Dark matter, with its head start in structure formation, created the scaffolding. Ordinary matter followed, funneled by dark matter's gravity. Gas accumulated in the filaments and nodes, cooling and condensing into galaxies. This process is called the cosmic web because the resulting structure resembles a three-dimensional spider web, or perhaps more accurately, the neural network of a brain. The resemblance is more than superficial. Both structures emerge from similar mathematical principles of network formation. Modern galaxy surveys have mapped the cosmic web in unprecedented detail. The Sloan Digital Sky Survey, the 2-degree field galaxy redshift survey, and others have measured positions of millions of galaxies, revealing the web's structure. The Sloan Digital Sky Survey, SDSS, deserves special mention. Beginning in 2000, SDSS has mapped over a quarter of the sky, measuring spectra and positions for millions of galaxies and quasars. The resulting three-dimensional map reveals the cosmic web in stunning detail filaments, stretching across hundreds of millions of light-years, voids so empty they contain almost nothing, clusters glowing with thousands of galaxies. More recent surveys have pushed even further. The Dark Energy Survey has mapped 300 million galaxies. The DESI Dark Energy Spectroscopic Instrument Survey is creating the most detailed 3D map of the universe ever made, targeting 35 million galaxies and quasars. These maps don't just show us where galaxies are, they reveal how the cosmic web evolved over billions of years, providing stringent tests of our cosmological models. The cosmic web also contains vast amounts of diffuse gas, the warm, hot, intergalactic medium that's been difficult to detect until recently. This gas, heated to millions of degrees, fills the filaments between galaxies. It represents a significant fraction of the universe's ordinary matter, and was effectively missing until X-ray and ultraviolet observations began detecting it. These observations match theoretical predictions and computer simulations remarkably well. The statistical properties of the cosmic web, the sizes of voids, the density of filaments, the mass of clusters, all match what simulations predict from the initial conditions encoded in the CMB. This agreement is a triumph of cosmology. Starting from quantum fluctuations during inflation, amplified by gravity, shaped by dark matter, cooled by ordinary matter physics, we can predict and observe the universe's large-scale structure. The theory works. Galaxy clusters deserve special attention. These are the largest gravitationally bound structures, collections of hundreds to thousands of galaxies embedded in vast halos of dark matter, surrounded by hot gas that glows in X-rays. The Virgo cluster, the nearest large cluster to us, contains over 1,300 galaxies in a region about 15 million light-years across. The Coma cluster, farther away, contains over 1,000 large galaxies and perhaps thousands of smaller ones. Clusters form at the nodes of the cosmic web, where filaments converge. Gas falling into clusters heats to tens of millions of degrees, emitting X-rays. This hot intracluster medium contains more mass than all the galaxies in the cluster combined, though both are dwarfed by the dark matter halo. Clusters are still growing today. They pull in galaxies from surrounding filaments, growing larger over time. But this growth is slowing. Dark energy's accelerating expansion is gradually isolating clusters from each other. In the far future, clusters will become island universes, isolated collections of galaxies surrounded by expanding emptiness. The cosmic web will dissolve as dark energy stretches the filaments beyond recognition. But that future is trillions of years away. For now, the cosmic web remains the universe's defining structure, a magnificent architecture built from quantum fluctuations, gravity, and 13.8 billion years of cosmic evolution. As we've traced cosmic history, two mysterious components have appeared repeatedly: dark matter and dark energy. Together, they comprise 95% of the universe, yet we don't know what they are. Dark matter was inferred from observations of galaxy rotation curves in the 1970s. Astronomer Vera Rubin measured how fast stars orbit in spiral galaxies. She expected stars farther from the center to move slower. Like planets in the solar system, Mercury orbits faster than Neptune. Instead, she found that stars far from galactic centers move just as fast as those near the center. This implies galaxies contain much more mass than visible stars, provide mass that doesn't emit light. Hence, dark matter. Further evidence comes from gravitational lensing, where massive objects bend light from background sources. Clusters of galaxies bend light more than their visible matter could account for, indicating substantial dark matter. The CMB also reveals dark matter through its influence on structure formation. The pattern of fluctuations depends on the universe's matter content. Fitting models to CMB data requires dark matter about 5 times more than ordinary matter. What is dark matter? We don't know. Leading candidates include WIMPs, weakly interacting, massive particles, hypothetical particles that interact only through gravity and the weak nuclear force. Despite decades of searching with sensitive detectors, we haven't found them. Experiments like LUX, Xenon, and PandaDex have placed ever tighter limits on WIMP properties, ruling out many theoretically favored candidates. Yet the search continues, because WIMPs remain one of the most elegant solutions to the dark matter puzzle. These detectors work by placing ultra-pure materials deep underground, shielded from cosmic rays and radioactive contamination. When a WIMP, if they exist, collides with an atomic nucleus in the detector, it should produce a tiny flash of light or a small amount of heat. So far, no definitive detections have been made, but the experiments grow more sensitive every year. Axions, extremely light particles proposed to solve problems in particle physics. Experiments are searching for them. The Axion Dark Matter Experiment, ADMX, uses powerful magnetic fields to convert axions into detectable photons. Other experiments search for solar axions or axions produced in the early universe. Axions could also explain certain mysteries in quantum chromodynamics, making them doubly attractive as a particle physics target. Primordial black holes, small black holes that formed in the early universe. They could be dark matter, though constraints from various observations suggest they can't account for all of it. Recent gravitational wave detections of merging black holes have revived interest in primordial black holes, as some of the detected black holes have masses that are difficult to explain through stellar evolution. Sterile neutrinos, hypothetical neutrinos that don't interact through the weak force, only through gravity. They could be heavier than ordinary neutrinos and might constitute dark matter. X-ray observations have searched for their decay signatures with tantalizing but inconclusive results. Or it might be something else entirely, a new type of particle we haven't imagined. Dark matter might interact through a dark force we haven't discovered, or it might exist in a dark sector with its own complex physics that doesn't affect ordinary matter except through gravity. Dark energy is even more mysterious. Discovered in 1998 through observations of distant supernovae, dark energy is a force causing the universe's expansion to accelerate. The discovery came from two independent teams, the Supernova Cosmology project, led by Saul Perlmutter, and the High Z Supernova Search team, led by Brian Schmidt and Adam Rees. Both teams were using Type Ia supernovae as standard candles, explosions of consistent brightness that can be used to measure cosmic distances. By observing how bright, distant supernovae appeared compared to their expected brightness, astronomers could determine how far away they were. Combining this with measurements of how fast they were receding from redshift, they could map the expansion history of the universe. The expectation was that expansion should be slowing down. Gravity, after all, is attractive. The mutual gravitational pull of all the matter in the universe should act as a cosmic brake, gradually decelerating the expansion. The only question was whether expansion would slow to a halt, reverse into a big crunch, or continue forever at an ever-decreasing rate. What they found shocked the scientific community. Distant supernovae were fainter than expected, meaning they were farther away than a decelerating universe would predict. The expansion wasn't slowing down, it was speeding up. Before 1998, cosmologists expected the expansion to slow over time due to gravity. Instead, observations showed it's speeding up. Something is counteracting gravity on cosmic scales, pushing space apart. This something is dark energy, comprising 68% of the universe's total energy. Its nature is unknown. The simplest explanation is Einstein's cosmological constant, a constant energy density inherent to space itself. As space expands, more dark energy appears, accelerating expansion. But why does the cosmological constant have the value we observe? It's far smaller than particle physics predicts by a factor of 10, 120, the worst prediction in physics. This is the cosmological constant problem. Alternatives to the cosmological constant include quintessence, a dynamic field whose energy changes over time or modifications to general relativity on cosmic scales. We don't know which, if any, is correct. Dark energy's discovery earned the 2011 Nobel Prize, but understanding it remains one of physics' greatest challenges. Together, dark matter and dark energy dominate the universe. Ordinary matter atoms, stars, planets, us, is just 5%, a minor component. We live in an invisible universe made mostly of things we don't understand. This is humbling, but also exciting. Discovering dark matter's nature or understanding dark energy would revolutionize physics, potentially revealing new fundamental forces or particles. After 13.8 billion years of evolution, the universe has reached its current state, vast, structured, and filled with wonders. Galaxies number in the hundreds of billions within the observable universe. Each contains millions to trillions of stars. Around many of those stars orbit planets, likely numbering in the trillions. Structure spans scales from planets to superclusters, forming a cosmic web shaped by dark matter and sculpted by gravity, radiation, and hydrodynamics. Star formation continues, though at a reduced pace. Stellar nurseries like the Orion Nebula birth new stars, while old stars die, enriching space with heavy elements. Life exists on at least one planet Earth and possibly elsewhere. Missions to Mars, Europa, and Enceladus search for life beyond Earth, while telescopes seek biosignatures in exoplanet atmospheres. We've measured cosmic parameters with percent-level precision. The universe's age, composition, expansion rate. We've mapped the CMB, traced the cosmic web, and reconstructed cosmic history from the Big Bang to today. Yet profound mysteries remain. What caused the Big Bang? What is dark matter? What is dark energy? Are there other universes? These questions drive current research. Looking forward, the universe's fate depends on dark energy. If dark energy remains constant, the cosmological constant scenario expansion will accelerate forever. Galaxy clusters will eventually become isolated islands in an expanding void. Star formation will cease as gas is exhausted. Stars will burn out. Eventually, even black holes will evaporate through Hawking radiation over 10–100 years. The universe will reach a heat-death maximum entropy, uniform temperature, no gradients to drive processes, a cold, dark, empty state. But this fate is trillions of years away. For now, the universe remains dynamic, vibrant, and full of possibilities. And through it all, from the initial singularity to today, the universe's evolution has been governed by physical laws we can understand, at least partially. The Big Bang theory, supported by overwhelming evidence, explains the origin and evolution of everything. Let us peer beyond the present, into the universe's far future. What destiny awaits the cosmos? The answer depends on dark energy, but if current models are correct, the future is long, strange, and ultimately dark. In 4 to 5 billion years, our Milky Way galaxy will collide with Andromeda, our nearest large galactic neighbor. The two galaxies are approaching at about 110 kilometers per second, and their collision is inevitable. But collision is misleading. Galaxies are mostly empty space. Individual stars will rarely collide, they're too small and too far apart. Instead, the galaxies will pass through each other, gravitationally disturbing each other's shapes. Over hundreds of millions of years, they'll merge into a single large elliptical galaxy, sometimes called Milkomeda or Milkdromeda. Our Sun, if still shining, will be flung to a new orbit in the merged galaxy, perhaps closer to the center, perhaps farther out. Night skies will look radically different, with the familiar constellations scrambled and new star patterns emerging. Meanwhile, the rest of the local group, the roughly 80 galaxies gravitationally bound to the Milky Way and Andromeda, will also merge over tens of billions of years, forming a single massive galaxy. But beyond the local group, galaxies are receding due to cosmic expansion. Dark energy is accelerating this expansion, pushing distant galaxies away faster and faster. In about 100 billion years, galaxies beyond the local group will have receded so far that their light can no longer reach us. They'll cross the cosmic horizon, disappearing from the observable universe. Future astronomers in Milkomeda will see only their local galaxy, a single island of stars in an otherwise empty, dark universe. The cosmic microwave background will fade to undetectable levels, redshifted to wavelengths longer than the observable universe. Evidence of the Big Bang will vanish. Future civilizations, if any exist, might never know the universe had a hot, dense beginning. The evidence will be gone. On even longer timescales, star formation will cease. The raw material for stars' hydrogen gas will be exhausted or dispersed. The last stars will form perhaps 100 trillion years from now, as red dwarfs slowly condense from the remnants of gas clouds. To appreciate this timescale, consider the universe is currently about 14 billion years old. The era of star formation will last perhaps 100 trillion years, about 7,000 times the current age of the universe. We are living in the very early morning of cosmic history, when the universe is young and bright. The last stars to form will be red dwarfs, small, cool, dim stars, less than half the sun's mass. Red dwarfs are miserly with their fuel, burning hydrogen so slowly they can shine for trillions of years. The smallest red dwarfs might live for 10 trillion years or more, 700 times longer than the universe has existed so far. As larger stars die and smaller ones persist, the stellar population will shift. Today, the Milky Way contains stars of all sizes, from red dwarfs to blue giants. In the distant future, only red dwarfs will remain, a fading population of dim, cool stars, growing ever fewer as even they eventually exhaust their fuel. Red dwarfs, the smallest and longest-lived stars, will shine for trillions of years. The universe will be dimmer, redder, and dominated by these tiny, cool stars. But eventually, even they will burn out. The last red dwarf will finally exhaust its hydrogen fuel and die, perhaps 100 trillion years from now. After that, no new stars can form, the fuel is gone. The universe will go dark. After the last stars die, the universe will enter the degenerate era. The only stellar remnants will be white dwarfs, neutron stars, and black holes. These objects don't shine, they're the cold corpses of dead stars. White dwarfs will slowly cool over quadrillions of years, fading from white to yellow to red to infrared to microwave to radio, approaching absolute zero asymptotically, but never quite reaching it. Neutron stars, incredibly dense objects where a sugar cube-sized piece weighs 1 billion tons, will also cool and darken. Planets will persist, orbiting dead stars or drifting freely through space. Some might retain heat from radioactive decay for billions of years, but eventually they too will cool. On even vaster timescales, 10, 34 years or more, protons might decay. The standard model of particle physics suggests protons are stable, but some extensions predict they decay with an incredibly long half-life. If so, all ordinary matter will eventually disintegrate. Black holes will be the last macroscopic objects to remain. They don't emit light, except for Hawking radiation, but they're incredibly long-lived. A stellar mass black hole takes about 1067 years to evaporate through Hawking radiation. A supermassive black hole at a galaxy's center might take 100 years. After the last black hole evaporates, the universe will contain only photons, neutrinos, electrons, and positrons, an incredibly dilute gas of particles spread across a space vastly larger than today's observable universe. This is the heat death. Maximum entropy, minimum energy gradients. No structures, no processes, no change. A cold, dark, eternal emptiness. Some physicists speculate about even further futures. Quantum fluctuations might occasionally create new particles, new structures, even new Big Bangs, though such events would be separated by timescales that dwarf even the 100 years of the black hole era. Others propose that the universe might be cyclical, eventually contracting and experiencing another Big Bang, or that our universe is just one of infinitely many, with new universes constantly nucleating from the quantum vacuum. These ideas remain speculative, but they remind us that our current era, the stelliferous era, when stars shine and structure exists, is a brief, bright moment in cosmic history. We live in a special time when the universe is young and active, filled with light and energy and possibility. As our journey through cosmic history draws to a close, let us reflect on what we've learned and what remains mysterious. The Big Bang Theory is one of humanity's greatest intellectual achievements. Starting from astronomical observations, the expansion of the universe, the cosmic microwave background, the abundances of light elements, we've reconstructed the universe's history from a fraction of a second after its birth to the present day, 13.8 billion years later. This reconstruction isn't speculation. It's a precise, quantitative theory that makes predictions, and those predictions have been confirmed repeatedly by observations. The CMB's temperature, its tiny fluctuations, the ratio of hydrogen to helium, the distribution of galaxies, the behavior of distant supernovae, all match theoretical predictions with stunning accuracy. We understand the physics of the universe from 1 second onward with high confidence. The first second remains more uncertain, though we have plausible theories. The very first moments, the Planck era, remain shrouded in mystery, awaiting a theory of quantum gravity. Yet for all our progress, profound questions remain. Why did the Big Bang happen? What, if anything, caused the universe to exist? These questions may be beyond science, or they may yield to future theories we haven't yet imagined. What is dark matter? Despite decades of searching, we haven't identified the particle or particles that constitute most of the universe's matter. It might be WIMPs, axions, primordial black holes, or something entirely unexpected. What is dark energy? The force accelerating cosmic expansion remains completely mysterious. We don't know if it's a cosmological constant, a dynamic field, or a sign that our theory of gravity needs modification. Are there other universes? The multiverse hypothesis, while speculative, emerges naturally from our best theories. If true, Our universe is just one of infinitely many, each with potentially different physical laws. Is there life elsewhere? The universe contains trillions of planets. Are we alone, or is life common? This question may be answered within our lifetimes, through detection of biosignatures on exoplanets or discovery of life in our own solar system. What is the ultimate fate of the universe? Will it end in heat death, a big rip, a big crunch, or something stranger? The answer depends on dark energy's nature, which we don't yet understand. These questions drive current research in cosmology, particle physics, and astrobiology. Each generation of telescopes, detectors, and experiments brings us closer to answers or reveals new mysteries we hadn't anticipated. Science is a journey without a final destination. Each discovery opens new questions. The Big Bang Theory, for all its success, is almost certainly incomplete. Future theories will deepen our understanding, perhaps revealing that our current picture is a special case of something more fundamental. But what we've learned is already profound. We know our cosmic origins. We understand how hydrogen and helium formed in the first minutes, how gravity built structure over billions of years, how stars forged heavy elements, how planets formed and life emerged. We know we are made of stardust atoms forged in stellar furnaces, scattered by supernovae, gathered into planets, and eventually assembled into thinking beings who can contemplate their own cosmic origins. This knowledge connects us to the universe in a deep way. We are not separate from the cosmos, but part of it, a way for the universe to know itself. In contemplating the Big Bang, we participate in the universe's self-reflection. We've journeyed from the beginning of time to the present, tracing the universe's evolution from an infinitely dense, hot state to the vast, cool cosmos we inhabit. We've seen inflation stretch quantum fluctuations into cosmic seeds. We've watched as energy condensed into particles, particles bound into nuclei, nuclei captured electrons to form atoms, and atoms gathered under gravity into stars and galaxies. We've witnessed the first stars ignite, forging heavy elements and ionizing space. We've seen galaxies form, merge, and evolve, building the cosmic web. And we've recognized that most of the universe, dark matter and dark energy, remains mysterious. The Big Bang Theory is science's greatest success story, a comprehensive account of cosmic history, tested and confirmed by observations across many domains. The CMB, light element abundances, large-scale structure, galaxy evolution, and more. It's also a story of profound beauty. The universe began as simplicity itself, a hot, uniform plasma, and through gravity and quantum mechanics evolved into the spectacular complexity we see: galaxies, stars, planets, and life. Every atom in your body was forged in a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all created in stellar furnaces billions of years ago, scattered by supernovae, gathered into new star systems, and eventually incorporated into Earth and life. We are made of stardust, the universe's way of knowing itself. As you drift to sleep, imagine the cosmic timeline compressed. In the first second, the universe transforms from a hot quark-gluon plasma into a hadron gas. Protons and neutrons appear. In the first 20 minutes, nucleosynthesis creates hydrogen and helium. For 380,000 years, the universe cools, waiting for atoms to form. At recombination, light is released, the CMB we see today. For hundreds of millions of years, darkness. Then the first stars ignite, ending the dark ages. Over billions of years, galaxies form, merge, and evolve. Stars live and die, enriching space with heavy elements. 13.8 billion years after the beginning, the universe contains us conscious beings contemplating our origin. And the universe continues expanding, evolving, changing. In this moment, you are part of an unbroken chain connecting back to the Big Bang. Every particle within you participated in that cosmic journey, from the first moments of creation to now. Rest well, knowing you are a child of the cosmos born from starlight, shaped by evolution, contemplating the ultimate origin. Tomorrow, you'll wake in a universe that began 13.8 billion years ago, a universe governed by laws that transformed a hot, dense state into galaxies, stars, planets, and life. The universe created us. Through us, it knows itself. And that's perhaps the most profound revelation of all, that the universe is not just a collection of dead matter, but a creative, evolving entity capable of producing consciousness, wonder, and understanding. Sweet dreams of cosmic origins, of quantum fluctuations becoming galaxies, of hydrogen fusing in stellar cores, of supernovae scattering elements, of atoms gathering into planets, of chemistry becoming biology, of biology becoming thought. As you drift deeper into sleep, let the vastness of cosmic time wash over you. The universe has been expanding for 13.8 billion years, and it will continue for trillions more. In this immense span, your life is but a flicker, yet that flicker contains the entire universe reflected in consciousness. The atoms in your body have journeyed through cosmic history. The hydrogen in your water molecules formed in the first minutes after the Big Bang. The carbon in your cells was forged in the cores of ancient stars. The iron in your blood was created in the violent death throes of supernovae. The gold in any jewelry you might wear was likely produced in the collision of neutron stars. You are not merely in the universe, you are of it. Every breath you take connects you to cosmic history. Every heartbeat pumps atoms that have traveled billions of light years and billions of years to be here, now, in you. The Big Bang wasn't just an explosion. It was the beginning of everything: matter, energy, space, time, and ultimately, consciousness. And it continues. The universe expands, stars are born, planets form, life emerges. The story of creation isn't finished, it's still being written, and we are part of it. As sleep embraces you, know that you rest in a universe that created you, that sustains you, and that through you contemplates its own magnificent existence. The cosmos dreams through us all. Good night, child of the stars. Dream of infinite spaces, ancient light, and the profound mystery of existence itself. May your sleep be as peaceful as the cosmic microwave background, the gentle, uniform glow that fills all of space, a lullaby from the universe's infancy that still whispers through the cosmos today.